Hello, everyone. Come on in. Let's see what's going on here. This was there. Admit all. Come on in, everyone. Anybody have any questions? Feel free to ask. We got 5 minutes before class starts. Yes.
Hello, sir.
Did you have a question, Kamna?
What is that? No, I did not. Yeah, you said something. I don't know if you were talking.
Oh, yes. I just asked if anybody had any questions. I'm sorry.
Oh, okay. I don't have a question.
No problem. We got about 4 minutes for class starts. You are welcome to ask away. Hopefully y'all figured out from the vector addition problem I did last time. Y'all got some sense of how to do that. When I make practice test 2 available, you'll see there's a lot of questions that entail vectors, little things like they'll give you a vector description and they'll ask you what's the X component, what's the Y component. Remember, your components, X and Y components, can actually have negative or positive values, whereas your actual magnitude of a vector is always positive. So you got to keep that in mind. And those are all precursor steps to adding vectors. And then, of course, multiplying vectors by scalars. There's a very specific thing that means. Subtracting vectors, that's a very specific thing that means. I've put a lot of links on your Canvas page to show those things and demonstrate them. But again, that's something you need to know how to do. Just for the record, though, if you multiply a scalar by a vector, let's assume the scalar is positive. Okay. If you assume the scalar is positive, then the direction doesn't change at all. But what happens is, let's say you multiply the vector by 3, whatever the magnitude is will now be 3 times that magnitude, but the direction will be exactly the same. If you happen to know the components, that means that each component will be increased by a factor of 3 as well. So if you had components of 2 meters and 3 meters, then the 2 meter component becomes 6 meters and the 3 meter component become 9 meters. If, however, you did try to multiply by a negative number like -3, then the magnitude changes again by a factor of 3. So if your magnitude was 5, now it'll be 15. But the direction, if it was 30, will now be 30 plus 180, which would be 110, or excuse me, 210, something like that. So that's what happens when you multiply by a negative number. You literally add 180 degrees to the angle that it's at, or you can say you just put the head pointing the opposite direction, or you can even subtract 180 degrees from it. Doesn't matter. Also, multiplying by -3 means that you're going to multiply each of the components by -3. So if the components were originally 2 meters and 3 meters, it'll now be -6 meters and -9 meters. So those are some common things you have to be able to do. If you multiply them by a number that's smaller than 1, if you multiply a vector by a number smaller than 1, then you're actually going to shrink the vector. So for instance, if you had a vector of magnitude 12 and you multiply by 1/3, well, now you have a vector of magnitude 4. Each of the components would also be decreased by a factor of 4. So if one component was 8, that one would become 2. And if another component was 12, that one would become 3. Of course, there's no guarantee that that's going to give you 12 because I was just making that up. But just want to give you a rough idea of all the things you can do with vectors. And hopefully you already know that from your pre-calculus or your trig section of pre-calculus and that sort of thing. It's still got about 1 more minute for the class starts. Anybody have any questions? I did do a addition of vectors problem for my lecture class today, my face-to-face lecture class. I probably am going to take and on the very last page of the notes for today, I'll at least draw those vectors and then write them out with their components and write out what their final answer was. So that's yet another example you'll have to adding it, because I don't think I'll have time to do that, plus all the other things I was planning on doing in today's lecture. So, all right, it's about
Professor, I
time to
had a quick
start.
question.
Yes, go for it. Is this Alex?
Sorry. Yeah, it's Alex. So this Sunday, the online tests and the chapter 3 stuff is all that's due, not the chapter 4 stuff.
Yeah, chapter 4, I'm definitely moving back. I'm not confirming those dates that you said, because I may or may not have changed them since then. But yes, chapter 4 is definitely being moved back. That
Okay,
part I
thank
know.
you.
Let me double check. The practice tests I've got listed. Oh yeah, this is 241. So yeah, you guys, your practice test and your regular test is supposed to be done by February 5th. And for some reason, your online test is not showing, and I don't know why. I mean, it's showing, but it's got the wrong date. So I'm going to have to fix that. That probably means that I'm going to move your online test to be due on the 7th as opposed to the 5th. Okay, so keep an eye on that. Oops, got 3 more people came in.
Oh, I also wanted to ask, where I know the test will be on Canvas, but will it be under modules or something, or will there be a new
Yes,
menu that pops
with
up?
my class, everything starts under modules. So if you go to modules, what you'll see, there's now a module that's called chapter practice, and there's, you know, a set of practice problems that every time you take them, they're different problems for each of the chapters. Then there's a module called practice tests. That's where you'll find your practice test. Then there's a module called online tests, and that's where you'll see test 1 is. Do not attempt to take it yet. It might be erroneous. In fact, I'm just going to unpublish it real quick, and I'll fix that tonight when we get when I get off of line. Anything else, anyone?
So you were talking about the chapter 3 homework? I missed that. I'm sorry.
Yeah, the chapter 3 homework, the new date's set on that, but the chapter 4 homework is definitely being pushed back. And I, you know, whatever the date is in my lab and mastering, that doesn't always mesh with the Canvas date. Always trust the date on my lab and mastering. But like I said, if you see a date that's really out of sorts, like, you know, so far we've covered chapters 1, 2, and some of 3. If you see a due date for chapter 7, that's tomorrow, obviously that's an error. So, you know, keep track of where we're at. We are currently in chapter 3, so I will at least keep it that real. Anything else?
Yeah, I'm just still having the issue with the grade book still saying like that I have zeros on assignments that you said if we did one of them not to do the other one, and those are still affecting
Yeah,
the
I
grade.
fixed that the other day. Specifically what I did was I went ahead and took everybody that had done, you know, 2 or had done parts from one or parts from the other. I took the highest score from each one of those assignments that were repeated and put it in a single column. And then I am going through the process and erasing the extra one. So that's gonna come up. There also seems to be some hidden, I don't know, old problems from the previous semester that I haven't quite figured out how to get rid of. I'll get rid of those, but don't worry. And you should never, of course, trust my grade calculations or Blackboard, or in this case, Canvas's grade calculation. You should really make yourself up your own spreadsheet and work that out, or actually just do it by hand, because that's the way I'm going to do. I'm going to probably do 2 or 3 students' grades by hand, and then check my Excel spreadsheet that I make. And if that matches my hand calculations, I'll compare it to Canvas. And then if Canvas matches, only then would I use Canvas. So if you're not familiar with how to calculate weighted average, now's a real good time to learn, and feel free to ask me. I don't mind helping on that. And that's definitely something you will learn now. I'm surprised at how few students really know their grades going into the final. I mean, I always knew exactly what my grade was, what I had to make a, you know, A, or what I had to do to make a B or whatever, all because I just calculated the weighted averages and stuff. So try to do that as much as you can. Also, I'm reminding everybody, all these videos are going up on my YouTube channel. So make sure you are okay with your name and or like probably even your face sometimes might come up if you ever show it. Otherwise, let me know. So I have to do some work to actually erase parts where you show up. I don't get much traffic, so and unless you're wanted for some major crimes or something cool like that, then you're probably just fine. A participant has enabled closed captioning. Who can see the transcript and recording on? I don't know why it says that like it's a question because it doesn't give me any option to answer it, but I'm okay with that. Yeah, I do. And actually, I was trying to make a transcript by itself, but for some reason, whatever I push doesn't do it automatically. All right. So we are well in
question.
chapter. Yes, go ahead.
What chapters the test one covers? 1, 2, and 3.
No, I do a test every 2 chapters generally. So this one will be
Okay.
just on chapters 1 and 2. I'm now going to make it do Tuesday night because
Okay.
I just noticed it's not up like it's supposed to be, even though I thought I fixed that 3 days ago. Somehow something was not done correctly. Maybe I did it to the wrong class. But I will give y'all until whatever the date of Tuesday at 11:59 p.m. is.
Professor Younger.
Yes.
I had a question about the grades and how they're percentage wise. It says on Canvas it's out of 145%, meaning if I miss 45% of the like portion, that it would be I would still have an A. I'm a little bit confused about that.
I don't know why it's saying 145%. I will check. That might be, remember I told you about those old assignments that are in there. If
Yeah.
it's got old assignments in there, it might even have old assignment setups in there. The syllabus spells exactly how it's supposed to be done. I've got to track that down. If it's saying anything like that, then it's probably reporting some absolute crap.
Yeah, it's saying that the concepts are like 45% of our grade or something.
Okay, yeah. So yeah, they're supposed to be 5%. That could have been something where I just accidentally my fat fingers hit a 4 and a 5 instead of just a 5. But I'll double check that. Your homework's supposed to be 20%, the concept's supposed to be 5%, and then your online test is like only 10%. And then 45% is your midterm and final. And they're like proctored or whatever, and your lab is 20%.
Okay, cool. Thank you for the clarification.
No problem. Sorry about that. And by the way, I do not put my syllabus in the little thing on the left-hand side of Canvas that says syllabus. It's actually in a module that says helpful documents. So I've had students that have been unable to find my syllabus and come to find out they've been expecting it to be in that little syllabus thing, which I haven't really figured out how to work it as neatly as I'd like to. So I suspect when I figure that out, it'll actually make the assignments disappear and appear better. I really blame that because I've got some assignments that keeps telling me to grade from 3 years ago. So something's going wrong somewhere, and I don't know. And I'm somewhat tech savvy. I'm like a software engineer and stuff like that. You'd think I could figure it out, but here I am. So. All right, so let's get started. So I've written down a couple problems that are sort of like problems that you'll see. In fact, they're modeled somewhat after, in some cases, examples from other books, examples from our book, or in some cases, questions that are in the test bank of other books or questions that are in the test bank for this book, so stuff like that. So I've got several of these problems I'd like to solve for you. Just so you can get the hang of it. And I'm trying to explain them in real time, so they tend to take a little bit longer than they otherwise should when you're solving them. So let me start by sharing my screen. And here it goes. And these I actually wrote, and I apologize for writing in cursive, but I discovered that handwriting without cursive is super time consuming. So I started writing back in cursive. So I'll read it to you because I know a lot of students aren't getting that training anymore. So this says the trajectory of object A is given by R sub A of T equals 3.00 meters per second T times I hat, which is the unit vector pointing in the X direction. plus 1.00 meters per second every second, parentheses t squared times j hat, which is the unit vector pointing in the y direction. And for object B, it is RB of t equals 4 meters per second t I hat minus 1 meter per second t squared j hat. What I'm asking is A, how far apart are objects A and B at t equal 5.00 seconds? B, determine the velocity of A as a function of time, and C, determine the acceleration of A as a function of time. So those are the questions. So let's start with our solution. Does everybody understand everything? Anybody have any questions on any of the wording that I just used? So what I need to do is the nature of vectors pointing to position sometimes is weird in that if I'm wanting to find the distance between them, if I don't pay close attention, I might actually give a smaller distance by accidentally doing it in the wrong order. So to prevent that, what I'm going to do is sort of write out RA of t and write out RB of t at each of these times, and then sort of graph them and get an idea of what we're talking about. So RA of 5.00 seconds. I think you guys can see all I'm going to do is take that t and replace it with 5. So I get 15 meters I hat. For RA, notice that it's just 5 times 3, but if the 5 had units of seconds, so that's why I've got meters left. And then 5 squared would be 25 seconds squared. So I get, in this case, plus 25.0 meters j hat. Okay, so that's RA at 5 seconds. Similarly, RB at 5.00 seconds is going to be, in this case, I got 4 times 5, so that's going to be 20.0 meters I hat. And then the other one I've got t squared again, so that's 25, but this time it's times -1. So it'll be minus 25.0 meters j hat. Okay. So in reality, you can sort of say that the positions are basically ordered pairs of 15.0 meters, comma, 25.0 meters. And for B, it is 20.0 meters, comma, negative 25.0 meters, like that. The distance formula, which we know from algebra 1, algebra 2, or whatever, is just D is equal to the square root, and the order doesn't matter. Just you're supposed to be consistent, but even then, when it's squared, it doesn't matter. I'm going to do 15.0 meters minus 20.0 meters, and I'm going to square that. Plus, I'm going to do 25.0 meters minus negative 25.0 meters. Square that, take the square root, and that should be my answer. So when I actually do this, I get 15 minus 20, and then I square that. That's 25 squared, and then I get 25 minus negative 25, which is in fact 50. So I'm going to say 50 squared plus the other answer is 25, and then I take the square root of that, and I get 50.25. 249, I should say. Okay, so that is the answer to part A. Anybody have any questions on that? You could actually take the time to plot that in space, but I think you can see that this is fairly reasonable just because their X coordinates are actually fairly close to each other. They only differ by about 5 meters, but their Y components are hugely far apart. So that's why that turned out that way. Now, does anybody have any idea how we go about doing part B? How do we go about finding velocity as a function of time if I have the position as a function of time? Does anyone know that? Hopefully you've also figured this out in lab. Like on a distance versus time curve, what's the velocity?
The slope.
The slope. And in this fast-paced world where you guys have had calculus, what do we use to calculate a slope?
The derivative.
Exactly. So V, oops. So V sub A of T is actually just, is actually just R sub A of T derivative with respect to time. So if I take the derivative of R sub A with respect to time, I think you can see what I get. It's basically 3.00 meters per second T, the derivative of that. Notice I hat, J hat, those things are truly constants. So if I took a derivative of that with respect to time and it had no T in it, the derivative of I hat is just 0. Okay. But in this case, it did have that. So it's going to become 3.00 meters per second I hat. And then the other one's going to become derivative of T squared is 2T. So instead of it becoming, instead of it being 1 meter per second, it's now going to be 2.0 meters per second times T, and then times J hat. So that's the velocity as a function of time. Any questions on that?
Then you would just insert 5 for T and then solve.
Yes, I didn't ask for that specifically, or at least I didn't try to. But yeah, if I wanted to know what the velocity is at 5 seconds, I could just put in 5 seconds for the time, and you'd see there'd be no change in the I hat velocity, the X component, but obviously the Y component would be 10 meters per second.
Wait, I'm sorry. I'm like super confused. Could you show that one more time?
Okay. The part I just talked about, or show you how I got the velocity?
The part B, the one you just showed.
Okay, so what I had to do is I had to go up and look at RA of T. That's this thing right here. You see that?
Yes.
So if you took the derivative of 3.00 T, what would you get?
3.
Yep, that's all that is. The only difference is I've got units now, and I've got an I hat that's got to be attached to it.
Oh,
So
so
it's
you
no-
just derived the top equation?
Yep, I just took the derivative of the top equation. And what would you get for 1T squared? What's the derivative of that?
2T.
Yeah, and that's where I got the 2.00 meters per second T. Just remember the meters per second, which are units, and the I hats and J hats, they're sort of like X's you'd have in a random number, only you don't differentiate with respect to them. So you just have to keep them in there and pay attention that way. But other than that, you can sort of ignore them. So I suspect everybody knows exactly what to do with regards to part C. Anybody want to give me some advice? The acceleration of object
The
A.
second derivative.
Exactly. The first derivative gives us the velocity. The second derivative gives us the acceleration. So I could write dv of A of T over dt, or I could even write d2 RA of T over dt squared. It's both the same thing though. It's just taking the derivative of the one that's in the red box immediately above it. So we can see that the derivative of 3.00 meters per second I hat, that derivative is 0. The derivative of 2.00 meters per second t is in fact just 2.00 meters per second every second j hat. So that's it. So, and these are, if you haven't seen it before, it can be daunting and scary. But to be honest with you, these are like the easy case scenarios. The harder case scenarios is like I did the other day when I gave you a as a function of t. I said like a with some number times t squared, I hat plus j plus some number times t j hat or something like that. And then I had to actually integrate to get the velocity as a function of time and use initial conditions to get rid of constants of integration. And then I had to integrate again to get the position as a function of time. Those are generally the more difficult ones. So just keep that in mind, but still, you want to know that this is something you are expected to do. And I just hate the way that turned out, that word solution. There you go.
Quick question, just for my own clarification. Is acceleration basically constant here? Is that why?
Yeah, you see, that's exactly the fact. Acceleration is a constant here. This is not unlike if you actually took the derivative of the trajectory vector, the r vector for a projectile. If you took the second derivative with respect to time, you would get the acceleration and you would get basically 9.8 meters per second pointing in the downward direction. If you happen to use a coordinate in which downward is negative, then it'd be a negative 9.8. If you happen to use a coordinate in which downward is positive, it'd be positive 9.8. But yep, that's it. It's a constant acceleration. Good thought. Notice how also the units are. You can write that as meters per second squared. I don't mind, but to me, I've learned that students generally get a slightly better understanding of acceleration when they recognize that 2.00 as meters per second, because I could ask you, okay, if that object started off with initial velocity of 0, how fast would it be going after 1 second? Anybody want to answer that?
Yeah, ask that again.
Yes. If the object A started with initial velocity of 0, how fast would it be going after 1 second, according to these equations?
2 meters per second.
2 meters per second. That's what 2 meters per second every second means. If I asked you for 2 seconds, you'd say, oh, well, it's going to go up another 2 meters per second. So it's now 4 meters per second. So that's why I'm doing that. Anybody else have any questions on this one before we move along? Okay, so these are very typical. I'm literally looking at problems from test banks, problems from examples in other books, problems from test banks within our own book, all sorts of good stuff. Here's a neat one I like. It says a ball rolls horizontally off a cliff at 5.00 meters per second. What I mean by that is the cliff is a perfectly level plateau, so that when the ball launches off the end of the cliff, it has no initial vertical velocity. Okay, so a ball rolls horizontally off a cliff at 5.00 meters per second. If it lands 40.0 meters from the base of the cliff, how high is the cliff? So this is another really good sort of projectile motion problem. Let me start off by drawing it and writing our solution. Feel free to give me any advice you think might be helpful. If you think you know some way to solve it or something like that, you can feel free to ask me. What I'm going to do right now is I'm going to say, okay, well, here's the problem I'm working on. It's a cliff. like that, that then has a huge drop, which I'm going to say is perfectly straight down and perfectly horizontally way out here somewhere. What's going to happen is I'm going to have this ball rolling at 5.00 meters per second horizontally. It's going to land way out here at 40.0 meters in, say, the X direction. Okay. What I would like to know is H equals question mark. Okay. So this is a good problem in the sense that, like I've been telling you, nature didn't have to do it this way, but it turns out that accelerations in the Y direction have no effect whatsoever on stuff going on in the X direction. So if you were in a perfect world where the sun was directly overhead at noon, and of course nearly infinitely far away, this ball would create a shadow on the ground that moves at exactly 5.00 meters per second horizontally. In other words, nothing's going to slow it down or speed it up, because the only acceleration it has, barring air resistance, is the acceleration in the vertical direction. So really all you need to know is, first off, how long does it take for an object to fall from a height h? And do we have a way of figuring that out? What I want to know is h, but what I do know is that 5 meters per second is how fast it's moving horizontally. So how many seconds does it take for the ball to actually move 40.0 meters to the right? Anyone?
8.
8, exactly. So what we're using here is an equation. You might know it as the average velocity. Average velocity is equal to x final minus x initial over time taken. So you could say x final is equal to x initial plus v bar t. But in this case, v bar is equal to a constant. So what we have now is 40.0 meters is equal to 0.0 meters. In other words, I'm pretending like my y-axis is at the cliff, because I didn't need to give it any initial position, plus 5.00 meters per second times t. And that t, of course, turns out to be 8.00 seconds. Okay. So now the question is, remember the ball, it was rolling off the cliff horizontally. So the fact that it was horizontal meant it had no initial upwards or downward velocity. So do you know of an equation that would tell us how far something goes if we know its acceleration, its time, and its initial velocity?
D equals a times t squared over 2.
Exactly. So, and I'll write it the way I derived it. I said x is equal to 1/2 a t squared plus v0 t plus x0. That's, a student asked me today, how do you know what equation to use, that sort of thing. And that's sort of an ongoing question. A good part of physics when you first start is about learning what each of the symbols mean that your instructor gives you in these equations. Sometimes it just comes down to, I know this quantity is A because it has units of meters per second every second, or it has units of meters per second squared. And that's fine too. While you're learning, that's what you're going to do. And then it's just a matter of looking for an equation that relates the things you know to the thing you want to know. But this is a college/university level physics course. So sometimes there will not be an equation that relates all the things you know to the thing that you want to know. You might actually have to solve for some intermediate thing, like the time I did here, to get the thing I really wanted, which was the height. Okay. But a lot of it really is just figuring out which equation to use based on not only what they told you, but what they imply. So like when something's dropped, that implies the initial vertical velocity 0. Unless they say otherwise, that also implies that the acceleration will be 9.8 meters per second every second downward. Obviously, if it's a different planet, then it'd have a different value, but stuff like that's implied. So in this case, we're going to do this, but we definitely have, I'm going to use it like a y. So I'm going to say y is equal to, and there's no need to call downward the negative direction. That just gives me a stupid negative that I could drop. So I'm just going to call it 1/2 gt squared plus 0 plus 0. So in other words, I'm treating my origin as if it's this spot right here at the edge of the cliff, and I'm pointing the y-axis downward. So now what I get is h, which is the thing we were looking for, takes the place of y, and that's equal to 1/2 times 9.80 meters per second every second times 8.00 seconds squared. And that gives me, with a little bit of math, 0.5 times 9.8 times 8 times 8. And that gives me 313.6 meters. Now, you know darn good and well, if this thing really did fall 313.6 meters, air resistance is definitely relevant. Okay. But there we are. Okay. But anyway, so that's actually it. Does anybody have any questions about that? That's extra sig fig, by the way. So that's a projectile motion problem that's not like the typical one where you launch and land at exactly the same height on perfectly level ground, which is what I derived in my face-to-face class, and it's also a derivation on my YouTube channel, but it's also a derivation in your textbook, so you can look at that if you want. But there are a lot of questions in the test bank that are like, a ball is fired over a horizontal ground at an angle of 50 degrees above the horizon with initial speed of 30 meters per second. How long will it be in the air? Or what's the max height it'll reach? Or how far from the launch point will it land? All of those are things that you can derive in general for an arbitrary velocity v at an arbitrary angle theta. And that's sort of what you'll find in some of my online videos on YouTube, as well as what you'll find in textbooks. Anybody have any questions on this before I move along? Okay. So we have another question that says a car is moving with a velocity of 3.0 meters per second. Notice that they're using x hat here and y hat. Okay. I, J, and K is what we use for X, Y, and Z. But sometimes people just use X hat, Y hat, and J hat, and that's perfectly fine. I like that because for some reason, when I first was introduced to I, J, and K, I couldn't remember which one was which, even though it seems to follow some pattern that's like an alphabet or something that exists. So you can always punt and just call it X hat, Y hat, and J and K hat, or X hat, Y hat, and Z hat if you want. So what it's saying is a car is moving with a velocity of 3.0 meters per second X hat plus 1.0 meters per second Y hat. And 3.5 seconds later, its velocity is 6.0 meters per second X hat minus 3.0 meters per second Y hat. And it wants to know what is the average, that's why the straight bars over top of the A, acceleration. And I want magnitude and direction, that's why the little arrows over the A. Okay. So in this case, the solution is just the definition of average acceleration. And the definition of average acceleration is just V final minus V initial divided by time taken. Okay. What I'm going to do is work it out that way, and then I'm going to actually get it in magnitude and direction format as well, so you have a little bit more of an appreciation for it. So A vector on average is V final, which would be 6.0 meters per second. Notice that's the Y component, or that's the X component. And these are like terms. 6.0 meters per second has an X, and 3.0 meters per second has an X. So in that sense, they're like terms. So I'm going to say 6.0 meters per second minus 3.0 meters per second, all that times X hat. And now I'm going to do the same thing with the Y hat. I'll say plus parentheses negative 3.0 meters per second minus 1.0 meters per second Y hat. And then all of this will be divided by the time taken. And what they told us was that the time elapsed was 3.5 seconds. Okay. So what I get is 6 minus 3, which is just 3. And then if I divide that 3 by 3.5, I get 0.8571. So 0.8571 meters per second X hat is the first component. And now I've got negative 3 minus 1. That gives me negative 4, and I divide that by 3.5. And that gives me minus 1.1429 meters per second every second, and that's in the Y direction. So if we worked out the details, you can see that 6 minus 3 gives you 1 decimal place. And then you divide it by 3.5. That only allows you 2 sig figs. So really, these 3 digits are all not significant. The other one, 3.0 minus 1.0, that only gives you 1 decimal place, and the numbers just over that, I divide it by 2 sig figs. So again, the 4, the 2, and the 9 are extra digits as well. Now, what does this mean? I've given you that A average vector is 0.8. Let's just call it 86, or let's call it 857. Whenever there's a 5, I carry that anyways. And that's meters per second in the X hat direction, minus 1.143 meters per second. That's in the Y hat direction. That's what our average velocity vector is, our average acceleration vector is. But to get some physical feel for it, what I realized is it has a positive X component and a negative Y component. So I should draw a coordinate system, which I'm going to draw now. And it's going to be this Y axis right here. And this X axis right here. So this is my X axis. This is my Y axis. And you see, of course, this is the negative side. Well, I know the X component is 0.857, and that actually points in the positive direction. So I'll use a nice green. Okay. So that's about 0.857. Now, in addition to that, I have a negative 1.143. That's actually in the negative direction, so I'm going to use a red vector for that. And I'm not too worried about being the scale, but enough to let me know whether it's bigger than 45 degrees or smaller than 45 degrees. That's all I do this for. That way I can just have some feel for what the answer should be. So when you add two vectors that are tail to tail, your job is to complete the parallelogram. So I'm imagining sliding that red vector without twisting it or shrinking it or stretching it. I'm imagining sliding it to the right until the tail of the red vector is at the head of the green vector. And that makes this line right here. Right? And then I imagine sliding the green vector without twisting it, compressing it, or stretching it until the tail of it hits the head of the red vector. Then I know that the actual answer is in fact drawn from the common tail to the head. That is my A vector average. Okay. The angle phi can be gotten by phi equals the inverse tangent of opposite, which is 1.143 over adjacent, which is 0.857. And now I take the inverse tangent of that. So inverse tangent of 1.143 divided by 0.857, close parentheses. That gives me 53.1 degrees. So in normal parlance from mathematics, that would be an angle of negative 53.1, because if you measure clockwise from the positive x-axis, that's a negative angle. If you measure counterclockwise, that's a positive angle. Now the magnitude of A, which I can write like just this, or I can just write like A with a bar over it, because when you write the symbol A without the vector symbol, that also means the magnitude. Well, in that case, it's going to be the square root of 0.857 meters per second squared plus 1.143 meters per second again squared. And in this case, I get 0.857 squared plus 1.143 squared. That gives me 2.04, and we'll take the square root of that. And that gives me 1.429. Meters per second. So in addition to this, you could say it's also equal to 1.429 meters per second every second at negative 53.1 degree. All of those versions are correct answers, barring any stupid mistake I might have made arithmetically or copying something down wrong. Any questions on that one?
I had just one question about the 0.857. Is the zero before that wouldn't count towards the sig figs, right?
Right, that doesn't count at all.
So if it's two sig figs, would it be 0.85 and then no line until
you
7?
should. Yeah, that one really should have been 0.85 and then the 7 underlined. What threw me off was when I do 6 minus 3, I only get 1 decimal place. So that's why I'd written the 8 there. But then once you do 6 minus 3, that's 3.0, and you divide that by 3.5, that means you get 2 sig figs. So yeah, I really should have written that as 0.85 without the 5 underlined.
Oh wait, actually no. Well, okay, yeah.
You see what I'm saying?
Yeah,
So yeah, I think
How-
I think you're right on that.
I'm not sure.
Yeah, well, that is part of the problem when you're doing this. It's what makes it difficult is when you add and subtract. So first off, I did have to do a subtraction. If that would have been like 5.1 subtracted from 6, that would have reduced me to exactly 1 sig fig, which would suck, right? But luckily, the 6 minus the 3 allowed me to still have a whole number plus 1 decimal place. So I actually had 2 sig figs in terms of multiplying and dividing. But in terms of adding and subtracting, I only have 1 decimal place. So when I then took the 3.0, which is what you get when you do 6.0 minus 3.0 and divide it by 3.5, that gave me 2 sig figs divided by 2 sig figs. So I could call that 0.85 and then just underline the 7. But
Okay.
yeah, that's good. You're thinking about the right stuff, even though I try my best never to grade you on sig figs, except for maybe a lab situation where it's specifically about a sig fig. Let's look at the other one, -3 minus 1. That would be -4.0. So that's 2 sig figs, and then I divide by 2 sig figs. Yeah, so that one really is supposed to be at the second decimal place. So it looks like the y component's correct.
Okay.
Anybody else have any questions? That's exactly the kind of stuff you guys are supposed to be thinking about as this semester goes, and in the next semester, we'll eventually get away from sig figs, even though the homework system's still going to use them, and we'll start going into propagation of error, which I've sort of hinted at already. Let's solve another problem. It is now 6:07. Okay. This one's kind of fun. It's a classic physics problem. You wish to save the life of a monkey. And I don't know, I seem to have written monkey with a extra like an R in front of the Y or something. I'll pretend like that's fixed now. So you wish to save the life of a monkey. The monkey is 30.0 meters high up a tree, and the base of that tree is 40.0 meters from the end of your tranquilizer gun, whose muzzle velocity is 30.0 meters per second. How should you aim the gun when you know the monkey will drop as soon as the gun is fired? Okay, so this is a neat problem. I've hinted at it before, and actually we're going to solve it. But first off, I'm going to draw the problem to make some sense of it. So here's our solution. What I'm going to draw is basically so this is 40.0 meters. And then I'm going to go 30.0 meters up here. Okay. And this is basically where the end of the rifle will be that we're firing. Okay. What I want to know is what angle theta I wish to fire. This one seems to be above the monkey. The monkey is literally right here, so I'll put the monkey right there. And we're assuming a point monkey. In other words, we don't have any room for error. This monkey is literally infinitesimally tall, infinitesimally wide, and infinitesimally thick. So we got to hit him right on the money. Okay. So what I can do is I can use my kinematic equations to relate all the stuff. So for instance, one thing we learned is that horizontal motion and vertical motion and projectile motion are completely separate. They behave entirely separately. So if I want to make an equation for the bullet, which is really a tranquilizer, but I'm going to use B because I don't like using T as a subscript, I can say that the Y position of the bullet as a function of time, if I assume the where the barrel is the initial height of 0, then I can use 1/2 AT squared plus V0T plus Y0, where Y0 is 0. I'm going to do that. And in fact, I'm going to say negative 9.8 because I'm assuming the y-axis pointing up is the positive direction. So the acceleration will be down and be the negative direction. And basically, I'm doing negative 1/2 of g. Well, half of g is 4.9. So I'm going to say negative 4.90 meters per second every second times t squared. Now it had an initial velocity upward, and that initial velocity is 30.0 meters per second times time, but I need the y component, so I have to say times the sine of theta. That will give me the actual y component. Does everybody see that? Is that obvious to everyone?
Yes.
Okay. So if this is, for instance, V, then this is V sine theta, and this is V cosine theta. Okay. So I've got that, and that literally gives me the position, the height of the bullet at any time t. And what we're assuming here is that at t equals 0, that's the time you pull the trigger. Now there's also an x of b. And remember what I told you about the shadow of a ball rolling off a cliff? Well, that's going to do the same thing as the shadow, again, of a perfect world where the sun's directly overhead. The shadow of this tranquilizer dart bullet thing that I'm calling is just going to be moving at a constant velocity to the right. And that constant velocity is 30.0 meters per second times the cosine of theta. So there, whoa. So 30.0 meters per second times time times the cosine theta. And I do that, I put the t in the middle because otherwise it's hard to tell whether I'm saying I'm taking the cosine of it or not. Now, what I've done is I've treated this point of the barrel as if it's the origin. So at t equals 0, the bullet is clearly at x equals 0, y equals 0. So you can see that's what the coordinate system for this is. Now I need to make a y position for the monkey. Can anybody think of what kinematic equation might be most useful for the monkey?
Just the free fall at negative 9.8.
Exactly. You're going to have the 9.8 in it. So you definitely need the acceleration.
GT squared over 2.
That's the one. There you go. So yeah, what I'm going to do is I'm going to say 1/2 of negative 9.8. Again, that's negative 4.90. Please don't think that I'm doing some magic here. I'm just avoiding a step by going ahead and multiplying the 1/2 by 9.8. Acceleration didn't change or anything. That's going to be t squared times that, because the monkey has no initial velocity. He's just going to let go of the limb when the bullet fired, or when he hears the bullet fire. He has no initial velocity, but he does have initial position, and that initial position is 30.0 meters. Okay, so that's the same thing as, again, y equals 1/2 a sub y t squared plus v0 sub y t plus y0. That's the equation I use for both yb and ym. Okay. Now what I'm going to do is I am going to label this equation 1. I'm going to label this equation 2, and I'm going to label this equation 3. And I am going to find T hit, which equals T sub H, the time it takes for the bullet to be vertically aligned. Can't remember if aligned has two L's in it or not. GNED with the monkey. Now, this is kind of weird. This is another problem where I do not have an equation that relates exactly the variable I want to exactly the variables I have. So what I'm going to do is I'm going to take equation 3 and I'm going to solve for T. And what I'm going to say is TH is in fact equal to XB. I actually want that to be 40 meters. So I'm going to say it's 40.0 meters divided by 30.0 meters per second times the cosine of theta, which equals essentially 4.00 seconds over 3.00 cosine theta. So I sort of have a time. That's the time at which it has to hit the monkey, right? But that time has a variable in it, theta. I just got to hope that that'll go away somehow. So now the other thing that has to be true, can anybody tell me what has to be true about, say, YB or Y sub M for the monkey to get hit? Can anybody guess what that might be?
They have to be equal.
Exactly. So we're going to set YB equal to YM, and we're going to do that at TH. That way everything will come into play. So YB equals YM at T equal TH. This is what we get. So YB is in fact negative 4.90 meters per second every second times T squared plus 30.0 meters per second. Oops, I shouldn't have done that way. Hold on, let me get rid of some stuff. Actually, I'll leave it right this up. I'll put the TH in a second. I'm gonna go ahead and play this out. You'll see why in a second. 30.0 meters per second times T times the sine of theta. That is YB. YM is negative 4.90 meters per second every second times T squared plus 30.0 meters. The reason why I'm not putting the TH in yet is you can see automatically the negative 4.9 T squared and the negative 4.9 T squared are just going to cancel each other out. So now I can go ahead and plug in the hit time. So this is going to be 30.0 meters per second times 4.00 seconds over 3.00 cosine theta times the sine of theta. So I just finished doing that term. This has got to be equal to, and I'll just show that was that. This has got to be equal to the other side. which is just 30.0 meters. I think you can see that when I take the 30 and I divide it by 3, that's going to give me 10 meters per second. And then when I multiply that by 4, that's going to give me 40 meters per second times second, or 40 meters. And sine over cosine is tangent theta. So tangent theta is going to equal, or let's try it this way.
Professor Younger,
Yes.
could you move the sheet so we could see the rest at the bottom?
Okay, so it was actually out of, yeah, it showed fine on my side. Sorry about that. And in fact, let me see. I thought there was an easier way to do that, but that just turned out horrible. I don't like that at all. Okay. So what I'm going to get on the left-hand side is in fact 40.0 meters tangent theta is equal to 30.0 meters. So ultimately, again, trying to get theta, which equals the inverse tangent of, as you can see from this expression, it's going to be 3 over 4. It's actually 30 over 40, but everything cancels out. So it's just inverse tangent of 3 over 4, which I think you know is 36.9 degrees probably. So let's do that just to make sure. I'm going to say on tangent inverse of 3 divided by 4 in parentheses gives me 36.87. We actually had 3 sig figs, so this is the only extra there, and that's degrees. So that's the actual answer, but I need to look back at this physically so you can understand what this answer is. So notice the triangle that goes from here to here is a 3, 4, 5 triangle. And the 3, 4, 5 triangle, in fact, has a 36.9 degree angle there. So in other words, you're supposed to aim it directly at the monkey. You don't want to, aim it under the monkey to try to compensate for the fact that he's going to drop. And the main reason is that it turns out gravity acts the same on an object shot upward as it does on an object that's dropped downwards. Any questions on that? So that's a typical problem that's done in this level course, and I like it. It's kind of neat, but in this case, I did it all with numbers. Hopefully that helped it be a little bit clearer to you. I usually work this in symbols, but I thought I'm doing too much of that, and my students probably need to see more numbers. So does anybody have any questions on this before I go to the next one? All right, looks like we're good then. So this one's kind of neat. An object is dropped from the height of a roof and shortly thereafter passes by the top of a 3.00 meter tall window. After an additional 0.45 seconds, the object passes by the bottom of the window. It's telling you basically that the object went the full 3 meters in 0.45 seconds. How high above the top of the window is the roof? So that's what they're asking me. So let me do solution. And in this case, I'll sort of draw it a little bit. So this is the roof. And that's the height of the roof, of course. And let's say this is the window. And this H is what I'm asking for. This distance, however, is 3.00 meters, like that. Okay. So what I know is my kinematic equations. And for instance, I know that, let me see, I'm trying to think there was a way I wanted to do it that I thought might be a little bit different from the way yeah, I think that'll work. What I'm going to do is play mostly with the velocities and then use the fact that I know gravitational acceleration is 9.8 meters per second every second. So what I'm going to say is the velocity of the object. So remember, we dropped some object. So the velocity of the object at the top of the window is equal to, I'm going to say down is the positive direction, so I don't have to deal with any negatives, 9.80 meters per second every second times t. And I'll call that t top. Okay. So whatever time it takes for it to get from the roof to the top edge of the window, that is gotten such that the final velocity at the top of that window would just be 9.80 times t top. Now the v at the bottom, which I'll just call v bot, okay, that's going to be 9.80 meters per second every second. But in this case, it's going to be t top plus 0.45 seconds. Does that make sense to everyone? Now, it might not be jumping out at you right now. How the heck is this going to give me distance? All you're telling me is velocity. Well, here's the trick. If I can figure out the average velocity that it travels across that window, then I can figure out v top and v bottom. So it turns out one of the kinematic equations that you can use when acceleration is a constant is that v bar is equal to v1 plus v2 over 2. In other words, you just take velocity at any time you call 1, take the velocity at any other time you call 2, add them together divided by 2. That's going to give you the average velocity over that interval. But we also know that v average is equal to distance divided by time. Well, that's exactly what I know. I know that the object went a distance of 3 meters in a time of 0.45 seconds. So what I can do is I can say v bar is equal to 3.00 meters over 0.45 seconds. That's my average velocity. But another way of doing my average velocity is doing v top plus v bottom over 2. So I'm going to say v top plus v bottom divided by 2. So I can do that now. I'm going to go ahead and divide 3 by 0.45. 3 divided by 0.45 gives me 6.667. So 6.667, carrying 1 extra sig fig, actually carrying 2 extra sig figs, meters per second is equal to, now the v top was 9.80 meters per second every second times t top. And then the v bottom was the same thing, 9.80 meters per second every second, only this time we're multiplying that by t top plus 0.45 seconds. Okay. And then I'm dividing all that by 2. So what I see right now is I should be able to take that 6.667, multiply that by 2, and then divide by 9.8, and that should help me closer to solving my equation. So I'm taking 2 times the 6.66. That's 13.3333. And now I'm dividing that by 9.8. And I get 1.3605. So 1.3605. I'll figure out what the digits are later, but I know for a fact those two aren't any good. That's meters per, well, wait a second. That would have been meters per second, but I ended up, I took meters per second, I multiplied by 2, that would have kept it as meters per second, but then I divided it by meters per second squared essentially. So that became second squared over meters times meters over second. So ultimately that just gives me seconds on this side. Now the other side is going to be 2 T top plus 0.45 seconds. So I can now at least solve for T top. So I'm going to take the 1.3605. I'm going to subtract 0.45. And then I'm going to divide by 2. So that I'll just have T top. So this is 0.9105. 4. Okay. And that should be seconds divided by 2 gives me T top is equal to 0.45527 seconds, giving you way more digits than really necessary. I suspect only 2 of those are good. We'll worry about that later, I guess. Now that I have that, that just tells me how long it took for the object to fall from the roof to the top of the window. But we know a formula that if you drop an object, you know its acceleration, you know its initial velocity, and you know its time. There's a kinematic equation that'll get us, tell us how far it moved. Anybody want to take a guess what kinematic equation that is?
Is that the v square, the second one versus equals the first one over the gravity times height?
Oh, you could do that, but that's yeah, that one's going to be, that'd be problematic because you'd need to find another velocity. I was thinking more in terms of what equation has, let's say X as a distance, A is an acceleration, T is a time. We know the initial velocity, so we can include that.
That would be 1/2 of AT squared plus V0 T plus
Exactly.
X0.
So in terms of Y, I'm going to write it Y equals 1/2 GT squared plus V0 YT plus Y0, only those are 0. So, and this one, in fact, is H, which is what we want to know. So I can now say that H is equal to 1/2 of 9.80 meters per second every second times 0.45527 seconds squared. So I'm going to square that number and then multiply it by 9.8 and then multiply it by 0.5. And that gives me 1.01.
Professor, I'm confused. Wasn't the time given in this equation already?
The time was only given for how long it took to go from the top of the window to the bottom of the window. That was the 0.45 seconds.
Okay.
That makes sense?
Yeah, okay, that's why I messed up then.
Gotcha. And actually it's weird. I've done it 3 times and I've gotten 3 different answers, so I'm really feeling confident. This one gave me 1.0156 meters is what it gave me. If I go back and look, let me see. I had 9.8. That's 3 sig figs. What I ended up doing was 3 divided by 2 sig figs. That only gave me 2. That'd be 6.6. Then I multiplied by 2. That still gave me 2 sig figs. Then I divided by 9.8. That still would have left me with just 2 sig figs. Which meant even this guy was not known. And then I subtracted 0.45 from that. I'm going to double check my math real quick. 1.3605 minus 0.45. That gives me 0.91054. That's exactly right. And that's equal to 2 times T top. So if I divide that by 2, I get 0.4525. So that looks like that's right. And that's really, of course, the time it took for it to fall from the roof height to the top of the window. So in fact, I should have, again, 2 sig figs. So it looks like all of these would be there. So I'm going to say the roof is a mere 1.01 meters above it. I got like 6 today when I did it. Actually, the good news is today, last night when I did it, I got the same answer I did this time. Today in class, I got a different answer. So I don't know what happened, but the physics is done right. There may or may not be a calculational error that I made a boo-boo on. I'm just not sure. 9.8 T plus, yeah, because there's no additional velocity there. T top plus 0.45, so that looks good. Yeah, everything looks fine here. So we'll leave it at that. Any questions on that particular problem? Okay, well, remember to go to my Google Docs and download this, because I'm going to write down some data from a vector addition problem I did in class today. I'll draw the vectors. I'll draw the table that I made for them, which I hardly ever do, but this time I just did once. And I just want y'all to have that as another solution to solving a vector addition problem. Anyways, we got about 2 minutes left. Let me see what the next problem is. I don't think that was something I could do in 2 minutes, but we'll check anyways. They say V is this at T equals 0, R is that at T equals 0, and they want to know what's R at 6 seconds. Okay, so this is actually a really good problem. What we would do with this one, I'll sort of outline it in the little bit of time that I have. And if anybody needs to leave, of course, you're welcome to go whenever. What I know is V is equal to dr over dt. So if I multiply both sides by dt, I can get v of t dt is equal to dr over dt dt. And then I integrate both sides. And this is going to be from r of 0 to r of t. And this side's just going to be from t equals 0 to t. So if I try to do that, I'm going to integrate v of t dt from 0 to t of, now in this case, I basically have a dr. So I have an r of t equals 1.00 meters I hat minus 1.00 meters j hat at t equals 0. You could, in principle, integrate that, and that'll add some new t's, and then you use the v data that was given above to figure out what any constants of integration were. There's definitely no way I'm going to be able to do this any justice in the time we have. So I'll just leave that one blank, but I will take on the next page, I will take the time to put the vector problem that I did in class today. So you folks are free to go. Thank you for coming. I will wait for the last person to leave in case anybody has any questions, but other than that, you're free to go. Anyone?
I have a question.
Yes.
So I was doing one of the problems on the practice
Uh-huh.
for the first chapter. I mean, I think it was for the first chapter. Not something hard, but I was just wondering if we supposed to know. I was asking for, let me see if I can the problem.
I'll stop sharing and I'll set it so you can share your screen if you want.
Oh, I already, when you finish the problem is it show different problems, right?
Oh, gotcha.
So, yeah, so
So this is the homework. This wasn't one of the practice tests or anything.
it was the practice test.
Oh, okay.
So it's asking for the coin, like how many coins can fit a box of. So are we supposed to know the dimension of coin? Because it didn't give any dimension for the coins.
Yeah, they expect you, part of what they expect you to do is understand, what's a millimeter, how big is a centimeter. I usually tell my students, a centimeter is about the width of my pinky nail, and a millimeter is about the thickness of the metal of a staple. You could also think that the width of a staple is about a centimeter, and then you estimate it based on that. So yeah, this very typical things. If, however, you have a problem like during a test and it says something like a quarter, and maybe you're not from, you've only been in the States for a couple months, you can ask me questions.
You get the point.
But yeah, you can make it up. But another rule on doing that is what I learned from Larry Weinstein over at ODU is try to take the smallest possible dimension of the coin that you think is even remotely reasonable. Maybe it's 1 millimeter, and then take the largest that it could possibly be. Maybe it's 10 centimeters. So, or excuse me, maybe that's 1 centimeter. So it's 1 centimeter and 0.1 centimeters, somewhere between those. If you multiply those two numbers and then take the square root, that's called the geometric mean, and you just use that. So if you can get an upper limit and a lower limit, you can just multiply the two limits, take the square root, and that'll give you an estimate of the size that you wanted. So you can do that for the thickness of a coin, then you can do it again for the diameter of the coin, or you can do it for the diameter of a grain of sand or whatever.
All right.
Okay, hopefully that'll help you. If it's something like on a test and you really don't know, just make sure you ask me. I think you probably at least on the midterm.
Okay, for online tests, let's say I get a problem.
You're allowed to Google. Yeah.
All right.
Yeah, you're allowed to Google.
All right. Thank you.
You're welcome. Anybody else? Randall?
Yes.
Video? Yes, Randall.
Yeah, the test that's coming up on the 7th or due on the 7th. You said that one's you can retake it multiple times.
The practice test you can take as many times as you want. The actual test, I usually give you 3 attempts and only keep your highest grade.
Okay. All right. Well, that works. Thank you.
No problem. Gavin, Brianna, anyone? Bueller.
I do have a question about the last problem we did.
Okay.
The V top and V bottom. I don't recall which equation you ended up using.
Okay. Yeah, that one, I actually used a lot of different equations, and in the algebra-based, oh crap, did the wrong share. In the algebra-based physics course, they know you don't know calculus. So they end up using an equation that's a little bit more obscure, which is the equation I just used. And that is that the average velocity, if the acceleration is constant, the average velocity is just v1 plus v2 over 2. So that's what you're seeing on the middle, slightly lower than middle on the right-hand side of this page. You see that v bar equals v1 plus v2 over 2?
Yes.
That's one of the kinematic equations that you're allowed to have on your sheet. But just like 1/2 at squared equation, that's only true if the acceleration is a constant.
Okay.
Okay.
But the v top where it shows the acceleration times t,
Right.
is that supposed to be the v equals initial velocity plus at? Is that supposed
Yeah,
to be
that's
that?
what that is.
Okay, so initial velocity was 0. And then the next one, the v bottom, that was the
It's still the
acceleration
same
times time.
equation. Yeah.
But we added.
Yeah, I'm still counting from t equals 0 being the instant it was dropped from the roof. So the v0 is still 0. And it's just 9.8 times, instead of t top, it's times t top plus 0.45 seconds.
Oh, I see what you did for t. T equals t top plus 0.45. Okay.
Yeah.
All right. And then going back to the question before that about the shooting the monkey.
Mhm.
Now, I did get lost when you threw the sign in there. So for YB, you had at the end times sine theta. Why did you add that?
Okay, so when we're dealing with projectile motion, we have a motion that's behaving independently in the vertical direction. That has an acceleration in the vertical direction, an initial velocity in the vertical direction, an initial height in the vertical direction. In order to get the component of velocity that's in the vertical direction, you have to take the velocity, which was 30 meters per second, and multiply that by the sine of theta to get the y component. That's why I drew the little red triangle on the left-hand side of this page.
Gotcha. Okay.
And the x one, that's, you'll notice, is a cosine in equation 3. That's for the same reason.
Okay. Now, for XB, we have 30 meters per second, t cosine theta. When we go down to just below that, t sub h, why does the t disappear?
Because I actually solved for the t. So I'm solving for t in equation 3.
So you just multiply
I
by.
renamed it t sub h because that's the time at which the monkey would be hit.
Okay, you just multiply both sides by t.
Okay,
gotcha. Okay.
That makes sense.
Yes, thank you very much.
No problem. Anybody else? All right, so I think we got a pretty good smattering of physics problems there. I'm going to leave this recording while I am adding the vector addition problem. You can try to solve this. Okay, you can solve that for extra credit if you want. But what I'm doing is I took a diagram. In my classroom and I drew it today. And then I used that to compute basically a vector, the sum of the vectors. So what I had was this coordinate system. I'm going to draw a y-axis there, an x-axis there. Okay, and I'm going to draw a vector right here, which is vector A, whose magnitude is 200.0 meters and whose angle right here is 30.0 degrees. I also had a vector. Obviously, I'm not trying too hard to do this to scale, but this vector B has a magnitude of 141.4 meters. And this angle right here is 45.0 degrees. I also had a vector here, which is C, and its magnitude is 250.0 meters. And this angle right here was 36.9 degrees. And then finally, I had this vector, which is vector D, whose magnitude is 200.0 meters and whose angle is 60 degrees. Now, what I made was a table, which again, that's something I normally only do for my algebra-based physics students, but in case anybody was feeling a little rusty, I figured I'd give them a try by showing them this. So what you do is you put the name of the vector in one column. And then you put the magnitude of the vector in another column. And then you put the angle of the vector in another column. And then you put the x component of the vector in another column. And then you put the y component of the vector in another column like that. Okay, and now my vectors will be A. Well, let me get off that. So it'll be vector A, which obviously had a 200.0 meter magnitude, and it had 30.0 degrees. Then there's vector B, which had a 141.4 meter magnitude and a 45.0 degree direction. Again, these directions are somewhat arbitrary. I'm just writing them down to have a record. Notice I didn't consistently measure them from the positive x-axis or anything, so that can be dicey. Here's C. C has a magnitude of 250.0 meters, and it's at 36.9 degrees. And here's D, and D has a magnitude of 200.0 meters, and it's acting at 60.0 degrees. Now, what I had my students decide, and you guys should do the same thing, is when doing this, exactly which components were positive or negative. So for instance, you'd say, A, is the X component positive or negative? What about the Y component? Is that positive or negative? So you guys should try to answer that before you actually look at this answer. So if you're watching this video right now, hit pause and you try to take a guess as to whether the X component of vector A is positive or negative, and then do the same thing for vector for the Y component. Then do the same thing for the B vector, then do the same thing for the C vector and the D vector. What I actually worked out was, in fact, plus 100.0 meters plus 173.2 meters minus 100.0 meters plus 100.0 meters minus 200.0 meters and then minus 150.0 meters. And then for D, I got minus, or excuse me, I got plus 100.0 meters and minus 173.2 meters. And then I can make another line right here and call this the resultant vector R, which equals A plus B plus C plus D. You can't put anything in these boxes, but what you're really doing is adding the VX column to get negative 100.0 meters and negative 50.0 meters, so that R, the resultant, turned out to be negative 100.0 meters I hat minus 50.0 meters J hat, which I also worked out to be 111.80 meters. And it turned out that that was measured downward from the counterclockwise. So I'll say this is at 26.57 degrees, and that's counterclockwise from the negative X axis. So in other words, when you make your coordinate system, there's your X, there's your Y. You can see that both X and Y are negative. The Y is actually a little shorter, so I'll say maybe this is 50.0 meters, and this is 100.0 meters. Completing the parallelogram, that gives us, of course, a vector from here to here. And this angle right here turns out to be 26.57 degrees. You can obviously see 111.80 meters is actually the square root of 100.0 meters squared plus 50.0 meters squared. That's where that came from. And phi equals the tangent inverse of, let's say, 50 over 100 gave me the 26.57 degrees. So that's another one, assuming, well, the class looked at it, I looked at it, I didn't find any errors. There may or may not be errors, but anyways, the main thing is you now have it. So I'm going to stop sharing the screen, and then I'm going to end the video. And once the video is processed, I will post it on my YouTube channel.